Okay, can you remind me what's special about a geometric sequence?
It's multiplication.
Yeah, you keep multiplying by the same thing every time. What do we call that thing that we multiply by every time? The common ratio. Okay, so we multiply by the same thing every time. Geometric sequence has a common ratio, and if you look back in your notes from last week, a term in a geometric sequence, a sub n, is a sub 1, the first term, times r raised to what exponent? N minus 1. Now think about what that means. If you're doing the first term, you're raising it to the 0. Like, it's just the first term. You're not going to multiply it yet, right? And then for the second term, you've multiplied by r 1 time. For the third term, you've multiplied by r 2 times. So if you're finding the 25th term, how many times have you multiplied by r? 24. So I'm going to write out, this one I'm going to derive our formula. We don't have a story like we did yesterday for Gauss. But I'm going to derive my formula by like writing out the series. Okay, so remember a series is different than a sequence because it's a sum of the terms. Okay. So in the geometric series, the first term is a sub 1. Yeah? And then I'm going to add, instead of writing a sub 2 here, let's just think about if I knew a sub 1 was 5 and my common ratio was 2, then to get my next term, don't I just do 5 times 2? 10. So in this one, I'm going to say a sub 1 times r. That's the second term. And the third term would be a sub 1 times r squared. And the fourth term would be a sub 1 r cubed. And then I'm just going to do a plus dot dot dot. That pattern continues, right? I just add another r because I got to multiply by another ratio. Now, this is where it gets a little bit tricky to think about. When I get to the end of my series, let's say this is a finite series, I have a sub 1 times r. If there were supposed to be n terms in the series, what's my exponent on the last ratio? So like in the second term, the exponent is 1. In the third term, the exponent is 2. In the fourth term, the exponent is 3. So what if I want the nth term? N minus 1, right? Take away 1, because it's always 1 less. This one is like r to the 0, which is 1. Okay. So I'm going to write, I'm going to put this at the end. A sub 1 times r to the n minus 1. It's just saying, like, I would multiply by 1 less ratio than the nth term for the nth term. Because I would start at the first term and then I start multiplying by ratio. So there's always 1 less. And I am going to put 1 right before that. If you know you end at n, so the last exponent is n minus 1, then the one before that is n minus 2. So if I'm trying to add up 24 terms, the last exponent will be 23, the second to last exponent will be 22, and then 21, and then 20, and then it'll work inwards. And eventually they meet right, but we don't know what n is. Okay, so I'm going to label this, all those terms added up. This is the sum of n terms. We saw that notation yesterday. Okay. When you're adding up the sum of n terms, the last exponent for your ratio is actually 1 less than n, because you started with the first term and you don't multiply by the ratio. Okay, let me ask this question. Say I want to do something to this equation to make it so that it does end at r sub n, or r to the n. What would I need to do to the whole equation to make this last one r to the n? R to the n minus 1 right now. What does it mean? Another r to the n minus 1. I want to make it r to the n. It needs another thing in the exponent to make it n, right? It's n minus 1. So how would you give it an extra exponent or an extra value in the exponent?
Plus 1.
Well, what are you going to do? So like if it was r cubed and you want it to be r to the 4th,
Multiplied by r.
if you add r cubed plus r, not like terms, you multiply it, right? You multiply that whole equation by r, everything moves up an exponent. So I'm going to do that. I'm allowed to do that mathematically, right? Multiply an equation by something, as long as I do it to both sides. Okay, so I'm going to say r times s sub n is equal to, and then I got to multiply this whole side by r, so every single term gets multiplied by r. This is now a sub 1 r plus a sub 1 r squared plus a sub 1 r cubed plus a sub 1 r to the 4th, right? These all got an extra r. I'm going to do plus dot dot dot. Now this one was n minus 2, but it gets an extra one, so now it's n minus 1. And this one was n minus 1, it gets an extra r, so now it's r to the n. So we're at a sub 1 r to the n. Now I won't ask you to derive the formula on your test or anything like that. I just want to show you why the formula is what it is. So just follow along as best you can. Don't worry if you're a little puzzled at all. That's not a big deal. Okay, so now I have two equations. Consider it like a system of equations. Okay, when you're solving systems of equations, you can solve through substitution or elimination, and these are kind of set up nicely for elimination. Okay, but what we want to do is have things cancel. So do you see like some of your terms match? Like you have an a sub 1 r in the top and you have an a sub 1 r in the bottom. In order for them to cancel with elimination, what will you be doing? Normally you add down. We would want to subtract. So I'm going to like stack these two equations. I'm going to put a minus sign right there. We're going to subtract down. Okay, so on the left side, I have s sub n minus r s sub n. Okay. On the right side, if I look at my top equation, I have this a sub 1. Do you have an a sub 1 to subtract down here all by its lonesome? No, so that's just going to be a sub 1 minus 0, a sub 1. Okay, then I have a sub 1 r minus a sub 1 r, gone. A sub 1 r squared minus a sub 1 r squared, gone. Gone. And notice, like, I don't have an a sub 1 r to the 4th, but is there really an a sub 1 r to the 4th if it goes that far? Yeah, so like this one's going to cancel. And this a sub 1 r to the n minus 2 is going to have one right before this one too. So that would cancel. And then the a sub 1 r to the n minus 1, a sub 1 r to the n minus 1. Okay, be careful on this one. Do you have an a sub 1 r to the n in the top? No, so when you subtract, you're really doing 0 minus a sub 1 r. A sub 1 r to the n. Okay. Well, that was nice. Now I have a lot less terms, don't I? Okay, and here's where our formula is going to show up. On both sides of this equation, they have something in common. On the left, what do the two terms have in common? The S sub n. So I'll factor out the S sub n. What's left over? 1 minus r. On this side, what do they have in common? A sub 1. So I'm going to factor out a sub 1. I get 1 minus r to the n. And we're trying to solve, like we did yesterday with the story of Gauss, for this formula for the series, the sum of all the numbers. So we want to get S sub n all by itself. Divide by 1 minus r. There's your formula. That's how it all works out. Now, as honor students, that's good for us to see, so we kind of like have seen something like this before. You know, when I give you formulas like the quadratic formula, I'm just not pulling it out of nowhere. It comes from real work. And we've now proven this formula will work for any finite geometric series, okay, where we have n terms. So, somewhere in your notes, make sure that you have that very clear. That's going to be your rule for the series. And that's this first one I have. Note that if we had written that, if we had rearranged the terms and written it so it was like a polynomial in standard form, where the highest exponent was first and the lowest exponent was later, you would come up with a different version of that, r to the n minus 1, r minus 1. Either one is fine. It doesn't matter. I guess I would add to these, maybe in my notes. I have it on the previous slide. But I put double parentheses, one in the top, one in the bottom, because since you're adding or subtracting in the numerator and the denominator, you really need to tell your calculator, this is the numerator, 1 minus r to the n. Do all of this first. This is the denominator, 1 minus r. Do all of this next. And last, divide them. If you don't tell the calculator that with parentheses, it won't know how to do it. Garbage in, garbage out, they say. So think about, if you want to do the sum of an arithmetic series yesterday, what we were working on in the number 62, we need n, the number of terms. We need a sub 1, the first term, and we need a sub n, the last term of the series. When you're doing a geometric series, you need the first term, you need the ratio, and you need the number of terms that you want to add, but you don't need the last term at all. Okay. So let's do some examples. Let's find the sum of the first 10 terms. Now, of course, at this point, we've talked about series on Monday. You could figure out the pattern and then manually calculate the sum of the first 10 terms, right? Find the first 10 terms and add them up. If you can recognize this as arithmetic or geometric, then you can use our shortcut formulas. So, what's the pattern that's happening from one term to the next? Divide by 2, okay? So we're going to say multiply by 1/2. Okay, so that means that's r, right? And that also means that this is geometric. So then I can use my geometric sum formula. The sum of the first 10 terms is equal to, in that formula I need a sub 1, 4. It's right there in front of my face, right? And then I need to do 1 minus r to the n. So what's my r? 1/2. Now you could do 0.5. If you're going to do 1/2 in your calculator, I'm not sure how those small calculators work with the fraction, but I would just encourage you, if you have negatives or fractions, put it in parentheses, just to be on the safe side. If you need them, then you have them. If you don't need them, then it's not a big deal. They're there, but they're not hurting anything. And we got to raise that one to the 10. And then we're going to divide by 1 minus 1/2. Okay, so see if you can type that into a calculator. Make sure everybody's practicing this. I won't help you on Friday with your calculator. That's on you to practice it. We should all get the same answer. Okay, so since you used a fraction, that fraction button, it's giving you a fraction. If you want, do you know how to change it into decimal? Yeah, so that's my answer, but either one is fine. Yeah. You got an answer?
Long round. Looks like you guys are doing a great job. Check with your pod members who I've checked with. You should have 7.9921875. How many people did it with the fraction button and then got a mixed number out? So what is that one? 7. It's and
127.
128. Okay, that's the same thing. That's fine. No big deal. I accept both of those. If you are having trouble getting that answer in your calculator, let us know. Ask your pod members about it. Ask me to come over and look at your calculator. We'll find out where you go wrong. Okay? Let's see. My next example. Am I on that? Where is that little pesky X? There it is. Okay. Or remember yesterday we practiced sometimes instead of me saying it to you in words and you looking for the pattern, we'll just give you a direction. Oh yeah, Chloe, if you want to borrow one of my calculators today, you can. I always think a cell phone calculator is the worst. I don't know how you guys feel about it, but I do not enjoy a cell phone calculator. The parentheses are hard to do, and then you can't see what you write. It really drives me bonkers. Okay, now remember, on your test on Friday, everything's going to be mixed together. How would you know, given this summation notation, that you could use the formula we just went over? What is n? 7. But why don't I use n divided by 2 times a sub 1 plus a sub n from yesterday? How do I decide which formula, or if I could even use the formula for a series?
Because you have a subtracting, right? In the power.
Because you have a rule. Yeah. And Izzy's looking at it like you have an exponent of n minus 1. That looks like which rule? Geometric. A sub 1 times r to the n minus 1. So something that you'll want to be thinking about in preparation for Friday is when I mix up all those summation notations on the test, how will you know which formula you're allowed to use? Based on what the rule says. If the rule looks linear, use the arithmetic formula. If the rule looks exponential with n minus 1, use the geometric formula. If it doesn't look like either of those, go back to Monday and you're going to manually be adding up terms. And I probably won't be giving you 25. Right? It'll be a small number of terms. You just have to find the 5 terms and add them up.
I'm gonna have to remember.
I'm going to give you the series formulas on your test. You'll come up with your own formulas or rules for sequences. You can know them, or you can just think about a sequence, right? But I'll give you the series. Okay, so let's do this one. This one's geometric. This is, like Kaylee said, the sum of 7 terms. What are we going to start a formula with?
3. A sub 1, which, hey, that's right there in the rule, right? 3 times 1 minus. Now, be really careful here. You can't make that plus 2. It needs to be minus a negative 2 to the 7th. You have to be real careful with your calculator if the ratio is negative. So again, if it's a fraction or it's a negative, I protect it with parentheses. And then divide by 1. It's not so big a deal here because you don't have an exponent. But I would still just get in the habit of protecting the ratio with another set of parentheses.
Why would it be 7 instead of 6?
Because you said that n was 7.
But then it's n minus 1.
It's n minus 1 in the rule, but look at your series formula we just wrote down. It's 1 minus r to the n.
Okay.
And that formula will be provided for you. I'll put it on the board. Okay, everybody type that in. Make sure everybody can get the right answer. I'll come around and check one person in your group. And we'll talk about infinite series here. You guys are doing a great job. Make sure your group gets the answer. I agree, Josh. I agree. Okay, now remember with geometric series, when you keep multiplying by something, it is possible to get some really big numbers. So sometimes series, like on your homework, might come out to be like 800,000 for the sum. That's fine. That's a valid answer. Or it could be really, really small. That's fine. That's an answer. Any questions about the geometric series that we've gone over so far? Okay, we got one other thing to talk about. An infinite geometric series. So we have kind of mentioned this just briefly. That like normally when you think about infinite series where you're adding up all the numbers, if the numbers keep getting bigger, like towards positive infinity, or the numbers keep getting smaller, like towards negative infinity, so more and more negative, that when you keep adding them, that sum just gets bigger and bigger and bigger, and it doesn't ever stop, right? So most series, infinite series, won't have sums. However, some geometric series that are infinite will have sums. And I'm going to tell the story of this guy walking to the door. Okay? So say this guy's over here and wants to walk over to the door, and he says, maybe he doesn't want to go to the door. Maybe he's got to go home and he knows he's going to be in trouble or something like that. So he says, I'll just walk half the distance to my door. And then once I get half the distance, then I'll walk half the distance again. Okay? So if he agrees to walk half the distance to his door, he's going to walk, right there? Okay? And then he's going to walk half the distance there. And then he's going to walk half the distance. And then he's going to walk half the distance. And then he's going to walk half the distance. And like that thing keeps getting smaller and smaller. And like I'm up here and I'm like, the door is right in front of my face. And I'm like, I'm still only going half the distance. It's a nano, whatever, right? Like I just moved. Did you see me move? And you're like, no, your face is up to the door. Do you all agree that at some point he basically walks, let's say the door is 10 feet away from him. He basically walks the full 10 feet. Okay. Yeah, at some point he starts by walking 5, and then he does 2.5, and then he does 1.25, and then he does half of that. And then at some point the increment is so small that you're like, dude, you're at the door. Right? Like, you gotta go inside. Time to go in. Okay? That's when an infinite geometric series will have a sum. So think about what your ratio is. What are you multiplying by every time? 1/2. If your ratio is less than 1, you'll have a sum for an infinite geometric series. So this will also be provided for you on test day on Friday. You don't need to know how to use the series formulas, when to use which one, but I will provide the formula for you. And it looks a lot like our other formula. It's just missing that other 1 minus r to the n. So it's just a sub 1 divided by 1 minus r. Now I have that note. That note's really important. If the ratio is not less than 1, or the absolute value of the ratio is not less than 1. So like if the ratio is -2, like our last one. If you keep multiplying by -2, that number just like flip-flops between positive and negative, really big numbers. And so it has no sum. If the ratio was -1/2 or -2/3 or -0.9, then there is a sum, because at some point that increment gets so small that we're basically to our sum. Okay, so even though we don't theoretically reach it, we say we're basically there. Okay, so an example like I might give you on the test would be something in summation notation. Okay. Notice, how would you know, looking at these summation notations, to use this formula I just gave you, a sub 1 over 1 minus r? The infinity at the top, right? This should stand out to you. Don't use the other two formulas if it's going to infinity. And stop yourself. Don't use the infinite geometric series unless it's actually going to, we call it converge. So what do you have to check before you plug it into the formula? You have to check your r, okay? So you notice it's infinity. Check absolute value of r is less than 1. Is there a sum for this one? Yeah, r is less than 1. Is there a sum for this one? Yeah, r is less than 1. If that's 5/4, do you do any work? Nope, you say no sum. Okay. So if I wanted to work this one out, the sum of infinite terms here is just the first term 3 divided by 1 minus 0.7. So what, 0.3 divided by 3/10, is that 10? That one should be in parentheses. And on this one, the sum is 2 divided by 1 minus 1/4. So that's 2 over 3/4. So what is that, 8/3? If I multiply by the reciprocal, 8/3. Alright, so you'll have a mix of problems. There's 2 pages on the homework assignment. The first page is where you should be using the first formulas we talked about because they're finite. And then the second page, you'll get just some practice with the summation notation. Any questions? I always like to imagine the story of the guy walking to the door. When I tell that story in pre-calculus, I do me walking to my desk. Just imagine, if you agree to walk a fraction of the distance, you could argue that you never actually get there. Try that with your parents and see if they enjoy it.
I mean, my parents can stop talking to me.
But